Resumes. We're ready to go. Welcome to Hopkins. Oh, this is a very nice day today, actually. It's not, the weather is always like this in Baltimore, and it's going to be here like this for the whole summer, so you guys are lucky. I don't think so, but let's hope. So I was tasked I volunteered to give a presentation on auditory speech production and auditory perception, and with an emphasis on the kinds of things that you guys will be doing in the workshop. So that's what I have done. Do they have probability yet or not? Okay, so in fact, actually, I figure out, before I can explain anything to you, because there's a little bit of researchy things here which are interesting, I wanted to say something about Bayes and Bayes inference, so there's even a Bayes primer in there, just to really get people going and understand what these probabilities and all these things that are going to be talking, and other people are going to be talking here. So anyway, my computer is waking up. Don't worry about that. That gets fixed. The moment it does a virus check, opens the file, we'll be ready to go. So and given that we lost some time, when do I finish, Sanjeev? When am I officially finishing? 12? No. 10:15. I'm going to steal, Nima, are you here? Okay. I'm going to steal some time from the lab to really finish my talk. Because I think it's important to get this done. Yeah, these are really tight schedule, and I really sincerely apologize for this. But I should have never agreed to give the first talk in the morning. I don't teach. I never really teach early in the morning because of exactly this. Okay, come on. Well, that was okay. So. Wake up. Okay. So this is the subject matter of my presentation: human audition and production in speech technologies. And as I advertised earlier, my goal is to give you a sense of what and where things that pertain to the auditory system and to actually the way humans communicate our speech production is relevant to speech technologies. It's a little bit, the scope of this talk is a little bit more broad than speech recognition or things of that sort, because I think it's important to understand where this world sits. So this is an outline of my talk. After a brief introduction, which is this, there would be a little bit of a primer on speech production. What is the primary means by which humans communicate? How do we produce sounds? Then 2 or 3 slides on the auditory systems. Then we'll get to perceptual attributes of speech and sound, things that we may have seen, may have heard, loudness scale, pitch scale. Then we talk a little bit about telephony, the kinds of things that are done today. They've been done since the mid-50s, and they are in practically every time you talk to a microphone, this is really the kind of things that you have. And then I will talk a little bit about, actually I'll talk a little bit more about automatic speech recognition and how some of the current state-of-the-art incorporates principles that principles of human physiology and speech perception. So, speech technologies. So, we have basically two classes of technologies. I mean, we're interested in speech, and you're here to learn something about speech and speech technologies. And there is things that have to do with precise restitution of information, like telephony and hearing aids. If you want to call your friend and you say hello, you want your friend to hear hello. And not only you want you to hear hello or her, but also you want him or her to hear hello and understand that that voice that's speaking on the other side is really John or Mary. You know, you don't want to hear a robot, hello, this is John. You know, I mean, that is really not a very natural, precise restitution information. So our goal of telephony is really to do that, to communicate on one-on-one basis, on multiple basis. Hearing aids, again, is one of these technologies that more often than not, it is really current hearing aids. It's about improving hearing for those who have lost or are deficient in that. And again, the goal is to take speech and reproduce speech as part of the early auditory system, and you'll see later where, so that people can hear their friends, they can hear the sound of a train coming or the sound of a car coming when they're crossing the road, and so on. Finally, speech synthesis is another very important application, and that the goal there is to produce speech from characters or from text, and again, very widely used many places today, from your GPS that talks to you when you're driving, to your machine that talks to you when you're trying to make online reservation and you're interacting with a computer. Now, the second class of applications of technologies for which the kind of things that we'll be talking today are relevant is that of automatic speech recognition, or ASR in short, and that is the task of really taking speech sounds in a natural environment or unnatural environment and producing a text representation of these speech sounds. That is also what I will discuss a bit today. And the second very big application today is that of in the second class, where the goal is not to really reproduce speech, but to extract something from speech which is relevant to your task, is automatic speaker identification. And you guys are fortunate to have today with us this afternoon, a whole afternoon, with probably who is the world expert, Doug Reynolds from MIT Lincoln Lab, is the world expert in that area. So you get first-hand coverage of that whole field this afternoon. Okay? Again, some of the things that I'll be talking today, they will be more or less relevant to the things that Doug will be talking this afternoon. Why is auditory, I mean, anybody, this is a natural question to ask. If we're going to build machines to understand speech or to do speech recognition or to help us communicate speech, why should we know anything about human perception and speech production? You know, why is this relevant? And that is actually not a unreasonable question to ask. Well, in telephony, which is really the precise restitution of information, hearing aids, etc., the ultimate consumer is you and me and humans. So if the ultimate consumer is humans, we better know something about how humans hear so we can produce sounds that actually sound like humans. And believe me, we are very sensitive to sounds, and especially speech, and we can tell the difference whether, I mean, making natural speech, for example, speech synthesis is very hard because of that issue. You don't want your friend to sound like, you know, some alien person in some very far planet. Now, the answering that question in an affirmative, why is it relevant, and I assume we agree it's relevant, for automatic speech recognition and speaker ID, it's harder. But it's become clear over the last 10, 15 years that indeed insights from the way humans process speech and humans produce speech indeed produce robust, help engineers, help us to produce machines that actually are better, are really solving automatic speech recognition problem, and to a certain extent speaker ID. And this is an argument that is an ongoing argument. It's been going on for the last quarter century, and partly the CLSP was founded, the Center for Language and Speech Processing, that's costing you now, which I co-founded about 15 years ago, was founded because the government was interested in exploring this aspect of speech recognition. Now we've gone beyond that. It's clear that building recognizers with ears, just putting ears on recognizers won't help us really make better speech recognizers, but at the same time, there is principles that we have uncovered, and colleagues of us, that really actually help machines do a better job in speech recognition. And it's still, this is really a hard problem to solve in a natural environment. Now, speech originates by your vocal tract, by your in the human speech production apparatus. This is a cross section of a person's head. You have the vocal tract, which is really the cavity in your mouth, and the combination of the tongue, the lips, and the glottis, which is somewhere here, which actually is responsible for producing speech. Speech propagates in air, goes to your ears, and from your ears goes to the various places to the cochlea, which is the organ of hearing. It gets transduced from pressure waves into electrical activity through the hair cells, and subsequently processed in the various nuclei and the auditory cortex of our brain to really produce what we seem to be aware or perceive as speech. Okay? Now, a lot of work has been done in all of these areas. Let me quickly go through the speech production. The key component in the vocal tract is the tongue. I bet you've never seen your tongue in a cross-sectional area. It's a very intricate structure, very muscular. It has multiple sets of muscles that control the shape and position, and that is how you control the cavity. Partly, mostly, how you control the cavity, which is responsible for producing the pressure waves that emanate from your lips and propagate in the air, and hence produce speech. The fact that actually we can do that, and you can produce things from a device like this, which looks like a pillow that you can actually move around in your mouth in a controllable way and up and down. It is really amazing, and there's a lot of work that's been done in the motor system to actually control the tongue. Just a few facts. The tongue has no bones or joints, and made entirely of soft tissue. This is really an amazing thing, and motion is accompanied by deformation. So the tongue not only moves, but it gets deformed, and that combination of motion and deformation is really very much responsible for the sounds that you produce. And without one or the other, trying to imitate some aspects of it, and your voice sounds terrible, okay? So, it is a muscular hydrostat, and like a squid, like an elephant trunk. I'm just going quickly through these things because I think we're running out of time. But actually, study of the tongue and how it really produces speech is really quite an exciting field. They have two, they have two definite sets of muscle hydrostats that actually produce orthogonal motion, and they are volume preserving. The total volume of the tongue is the same, and it moves around, and the size is constant. Your tongue doesn't get really big or small. It pretty much stays the same, but moves back and forth and also gets deformed. And you don't even know that you're doing it. I have a video to show, but I think we'll skip the video because it's going to take another 2 or 3 minutes. And as I said, it's like a pillow or like a water bird, where you actually press somewhere and you pinch somewhere, and then you get a bump somewhere else. So that is really how you produce speech. And this is the physical structure that produces speech, together with the glottis and your lips, and you have a whole brain actually that controls it, and that's really so. This is some nice pictures from Maureen Stone. Turns out that and her collaborators. Turns out that one of the world's experts in tongue motion, movement, and characterization and modeling actually is in Baltimore. Her name is Maureen Stone at the University of Maryland downtown. And so there is what I have here. What I show here is two sets of muscular layers, fibers that actually are interweaved. I think we'll skip the anatomy and move on. And we can have the way the tongue is studied, and the way the tongue is studied in relation to speech production. You take an ultrasound transducer, the way people study the heart or babies in pregnant women, and then you can actually get a picture, dynamical picture, cross-section of the tongue as it moves. You can put it from bottom, you can put it on the side, and so on. And there is, if we have time later, I'll put the video on the web so you guys can play the video and have fun with this. Now, as I said, was responsible for making sound is really a resonator structure. A resonator structure is typically a tube that has, much like any wind instrument, that can have an open front or an open back, and you excite it at one end, and you get resonances and you get rich sounds, as I said, like a wind instrument. Now, instead of the tongue, so how do you change the structure of the sound, the pitch, and so on of the wind instrument? You play the keys, and the keys open and close the tube, make it longer or shorter, and that's how you actually make the sounds that you want to play. Now, in our vocal tract apparatus, we do all of this plus more. So you have the area where you excite the vocal tract using the glottis, which basically takes DC signals and produce an AC signal. If you think about it, how can we start producing periodic waves without having an oscillator? It's not that we can go to Radio Shack and buy an oscillator and plug it in and make sound, you know. So someone has to make an oscillator. So how do you get a varying signal out of a DC quantity? Well, turns out you build pressure in your in your lungs, okay? And the glottis actually, it's a highly nonlinear mechanical structure, electrical too, because there is some feedback there, that actually takes that DC pressure and produces an AC wave out of it, much like the reed in your wind instrument, where you actually you put pressure and then it vibrates. So the same principle. So we solve one of the problems, how to produce these time-changing waveforms, because unless you have time-changing waveforms, you don't have waves, and unless you have waves, you cannot propagate the sound, and if you don't propagate the sound, you won't be able to communicate. So this is really essential, and that happens at the glottis. Then you have the whole vocal tract that is controlled by the motion of the tongue and the jaw as you speak. These things go up and down in addition to my tongue moving inside, and also my lips. If I clamp my lips, you can tell something, but it's not very intelligible. Okay, so there's a lot of moving components in it, and typically when it comes to modeling, we model a cross-section. We assume that actually we have a uniform tube, and we'll model the cross-section of the tube, although that is not true. The tongue actually not only moves up and down and modulates the tube in the sagittal device, but it also moves in this way and in this way, and those motions actually are responsible for some of the very fine sounds that we produce. This is really, this is what I was saying earlier. This is really a shape of the tongue if you were to look at it from top, and for run and rang and very similar sounding sounds, okay? But you can see how the shape of the tongue actually is a bit different, although one can argue the main difference is that the tongue is kind of backwards in this case as opposed to that. You can see the shape of the tongue. This is really a cross-section of the tongue this way. This way. At one point, it ran a lot. So this is really from run a lot. You get the tongue to be deformed in various ways, including asymmetric ways that you see here. So the tongue looks like it's tipped on one side. It makes a little hole, and then this tip actually moves towards the middle as you go out of the run a lot, and then that's the stop. Anyway, so this is really about tongue, and by now you'd be wondering, gee, if I were to start thinking about the tongue and how it produces sounds, I'm lost. Can we get anywhere? And the answer is yes, we can. And this is really where the engineering comes in. We have the anatomy, the physiology, the study of the tongue muscle groups. Now engineering comes in and says, okay, well, let's assume that the tongue is modeled as the tongue, the vocal tract that is modulated by the tongue and the lips as a tube, and let's say a tube, a open-ended tube where one side is closed and the other side is open, of length L. We'll have resonances which are given by this formula here. This is Helmholtz equation, some basically written down many years ago, and where C is the velocity of sound, 35,000 centimeters per second. That's C, and L, and N is the mode. And so if we actually do that, and we we take a tube which is roughly 17 centimeters, which is roughly the length of your vocal tract, or a nominal length of the vocal tract. Turns out different people have different lengths, as you can imagine. And turns out, just as a tidbit, I'll see how far we can go today, but the fact that different people have different lengths and therefore produce speech that sounds a little bit different from one person to another, you can actually exploit that prior knowledge, you can actually exploit, and you can help machines do better in speech recognition. That's something called vocal tract normalization that I myself and two colleagues invented 1994, and that is really a very simple idea that gave an amazing improvement in automatic speech recognition, and based on this thought that different people can have different vocal tract length, and if you can predict that vocal tract length more or less a priori, then you can use it as part of your system to really improve the speech recognition. Going back to how the vocal tract length and shape affects production of sounds. Well, if we take a tube, just an open-ended tube, a uniform tube, and of length L, then what we're going to get basically, and we see the sound that gets produced out at the end of the tube. We're going to, well, if we look at the resonances of this tube with sound using this formula here, we're going to find out that we have resonances at roughly 500, 1500, and so on, 1, 2, 3, where all these peaks now are multiple integers of n to n minus 1 is really the mode. So not surprising, a tube with it open at one side and closed at another side will sound like a wind instrument with a very pure tone and overtones, and harmonics of that tone, and that's really what you actually get. You get a rich sound that comprises a fundamental and some harmonic content at different frequencies. Now, okay, so we started with a very simple model now, that of a uniform tube. Now, the next question, which is really what Wakita did in 1974, which is a really brilliant piece of work, says, okay, let's take the tube now, and based on the kind of measurements that we saw in the previous slides, let's now take those cross sections of the vocal tract, which is modulated by the tank, and let's see if we can actually take our simple tube and produce now things that sound like phones, so sound like sounds that humans make. Interesting idea. So what you see here is the cross section of the tube. In this case here, you modulate the cross section. Instead of being uniform, that width, it gets modulated, and what happens now, in this instance here, the tube actually has been shortened. Now you have a tube which is actually roughly 3/4 shortened, and so it will produce things which are, which, if I look at the first resonance, which in principle, since the tube now is shorter, it will seem that the first resonance will go lower frequency. The tube is shorter. The first resonance should go to a higher frequency. But this is probably something that we don't see very well in this picture. Much like that, the tubes are not completely closed. Actually, there is a little bit an orifice there that actually is responsible for some of the effects that you see. At any rate, if we take a tube and we modulate it, we shape it so that it mimics the way the vocal tract is, as recorded by the measurements that I showed in the previous slides, then we can begin to see sounds like resonances of the vocal tract. These are what we call formants that actually correspond to various sounds, u, o, e. Okay, so if you take now this tube and you modulate it as this in time, in principle now you're beginning to produce sounds that sound like speech, okay? And that is actually a very interesting result. Actually, from very simple physics, you can begin to reproduce things that sound like speech, or basic components of speech. Now, of course, the story is not as simple as you as you think. Actually, what's happening here now? There is indeed a. I can see it better on my laptop. You cannot see it here. There is indeed, in the example I tried to describe here, you actually have two cavities. You have a cavity which is closed on both sides, and you have a cavity, a smaller cavity that is open on one side and reduced, excited at the right here with a very, very, very small amount of flow. So what you see basically here is the interaction of two cavities, and similarly on the first panel on U, clearly now you have actually two segments, two tubes. One tube has a length which is L over third, and the other tube has a length which is 2L over 2/3 L, you know, and now they are coupled together with a small orifice, and that really what produces actually the complex resonances that you have there, which is interactions also, where you can see some interactions between the fundamental first order resonances. So the bottom line is that here we have a system that actually can produce speech, and if we actually look at the vocal tract resonances, and we look at, which are going to be called formants, and we can actually look at formants for different F1 versus F2. You know, the first resonance plotted as a function of the second resonance. Basically, it's a two-dimensional representation of the first peak in the previous. Let's get a good one. This will be a good one. The first resonance will be here, and the second resonance will be right here. Okay, this will be F1 and F2. This is very clear for that. So if we take that and we actually analyze speech sounds, we see now that, and this is another very famous result produced by Patterson and Barney. That's why this is called the Patterson and Barney diagram. What you see actually is that formants, these resonances of the vocal tract, actually produce a graph, produce a partitioning space where you actually have different areas partitioned, clustered together. So for different sounds. So all the the way we represent here is that the dot, the star represents the mean, and the length of the line here represents the variance in the variance, the contribution to variance in the primary dimension. So basically, you get a sense how spread these things are and what direction they are spread, and they are really, in this case, they are ellipsoids, for example, going like this, going like this, going like this. Okay, that's really what the representations there said. This basically tells you, and forget for a second the second plot there, that if you actually plot these formants, these resonances, that these resonances tell us something about sounds, and they are sufficiently spread apart, so by looking at the resonances, in principle, you should be able to tell the difference, which is F1, F2, you should be able to tell the difference between E and A. Okay, or A. What do you say? A. Okay? So this is really interesting. Now, this is done with control experiments in a lab. We say, well, let's try to reproduce. Okay, so this is really perceptual psychophysics will do. We'll take people, we'll give them a task, and you record data, and now you plot the data, and you say, aha, I figure out a universal, and that is basically all 4 months fall into what is actually known as the hand pattern, where you have this basically the 4 months being the for various sounds being clustered in kind of classes that look like a hand. Well, we went on and we said, okay, let's reproduce these experiments now with real data. I mean, these are still control experiments. And we actually, Teresa Kamm, a few years ago, more than a few years ago, did an independent, it was a graduate student in my group, did a study where we said, let's look at lots of data available as databases, and let's plot the data. And you can tell that the second plot there is not as the clusters of F1, F2 classes are not as well separated in the F1, F2 space as in here. And actually, this is really a good sequel to many things I would say earlier, is that, well, this is interesting. And the difference between this and that is that in this case here, people were asked to just talk and read, actually. Timid, it is really a rather clean database. It's not even natural sound. I mean, it is natural sounds, but you're asked to it's pretty scripted. You're reading from somewhere, so you're producing speech in a controlled way, and not like when I'm talking now or lecturing now. So the bottom line is that natural speech in environments that we actually use to communicate is very rarely clean, or things are not as clean as possible. What does it mean here? It means that actually, as we produce speech, the resonances of vocal tract are not very well formed. I mean, so that would be really making myself produce resonances which are well controlled, but rather they're kind of sloppy and rather unseparable. So yet there's enough information there for us to really move on and really use this in our system. Now, the auditory system, we talk about production. Let's talk about the brain. I thought this should be a really 3-hour talk. It used to be longer talk. So let me actually describe this. This is a complex panel, but let me start on here. So now, in principle, given that we agree that based on the vocal tract, and 4 months, F1, F2, and 3, if I can combine these 4 months together in the right way, I should be able to produce things that sound like speech. So let's start with a very simple sound, a consonant vowel, ba, ba, ba. Now, I can synthesize ba by taking sounds, let's say sine waves, okay, and F naught is the fundamental. It's actually it's a characteristic of your excitation system, and F1, F2, F3 are the formants, are the resonances of the formant of the vocal tract, the peaks. Remember the little peaks? If I give you the temporal trajectories of the formant resonances, this is from 0 to 100 to 80 milliseconds, and what you see, the straight lines. So for example, for ba, the first formant for b starts at 0, and the frequency increases to about what? That's about 500 hertz, and that stays constant. For the second formant, again, it goes up and increases and stays constant. And the third formant, as you're building ba, it also increases and stays constant right about 50 milliseconds. So if you actually take these formants, you can synthesize a sound like ba. You can combine them together, and you can get the waveform that actually sits on top. So you can actually synthesize speech that sounds, you can synthesize waveforms now that sound like speech. In this case, a CD, consonant, vowel, b, a, okay? Now, then you can take that waveform and put it in the ear of a cat. You go through the cochlea where you transfuse the data, and you can record from the auditory fiber. And this is really some of the, this is an amazing set of experiments first done here at Hopkins by Eric Young. Eric Young is a professor of biomedical engineering department, and Young and Sachs. Professor Sachs used to be the director of biomedical engineering program here. He retired a few years ago. But basically what they did, they managed to keep the cat alive for 2 or 3 days. And they recorded signals from the auditory nerve, from the wires coming out of the cochlea, as they presented the cat the sounds. And what you can see, this is time. This is actually real data plotted from their data. I mean, this is the graph plotted from their results. And what you see here in the amplitude is let's say is the post-stimulus histogram, which think of it as you have the neural fibers and they have the fire action potential. Think of it as the probability of actually the fiber firing at a given time after you presented the stimulus. If you look back, what you can see different patterns in the auditory fibers, and clearly this is going from low frequency to high frequencies. And what you can, if we can turn the lights off, and this is kind of, I'm not going to do it because then the whole thing turns off. So avoid that. But what you can see is different fibers, different wires, so to speak, neural wires coming out of the ear, going to the brain, encode different aspects of the stimulus. And in this case here, these fibers, each one of these is a fiber, recorded from the, I mean, this is really an amazing experiment, okay? They kept the cat there for many, 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 many hours. So this set of fibers record the fundamental. These fibers record the first formant, second formant, third formant. If you look at the spacing, for example, from here to here, from here to here, from here to here, from here to here, and so on, it will correspond to this frequency here and going down. And indeed, you can verify that this spacing here is a little bit bigger than this spacing here, no, the other way around. This spacing here is a little bit bigger than this spacing here as the frequency went down, because it's a temporal waveform, okay? I tried to say the wrong thing, tried to fake it, but it doesn't work, So anyway, the bottom line is that what's happening in your auditory system, in your fibers, you encode actually frequencies with set of fibers that then go to the cortex. Now, what happens next? Okay, so this is just very early in the auditory system, and this is how the sounds that we hear are represented. Speech sounds-like sounds are represented in the auditory system. What happens next? You go to after many nuclei that do, among other things, finding where the sound came from and making a three-dimensional representation of the sound, because unlike we don't have a sense of where the sound is, so we have to actually build it in our brain. Then you go to the auditory cortex, and basically this is again a complicated panel that shows how the various vowels O, I, A, E, E are represented and back, central, front, and central and mid and open correspond to how you actually produce them. That's really related to the production. In time and in frequency, in your cortex is represented as a temporal spatial, a frequency time map where each one of these panels is sufficiently distinct from each other. You can see, for example, the A from the O, the E from the A, and so on. Now, turns out that this is work done by Shihab, and this is really actually the thesis of Nima. Nima is the TA that's going to do the lab with you this afternoon. So if you, I put this up here just to tease you. If you have questions on this representation, maybe you can ask Nima to give you a little tutorial on that. This is really groundbreaking work, and again, you're fortunate to actually have one of the world's experts actually doing the tutorial this afternoon, this morning actually after my talk. Now, someone may say, well, you know, you talk about resonances of the vocal tract. How about things that, how about fricatives and consonants? So this is a similar map for the consonants, and like b, g, d. Okay. Still, you have representation in the auditory cortex, which is different than what you have for vowels. And remember now is that each one of these panels has a scale of about 100 milliseconds. As you produce speech, you really think of it as little panels of these auditory panels where the best frequency and time interact to actually produce and represent the complex auditory sounds in your system. I would be surprised if actually Nima doesn't, as part of his assignment, doesn't ask you to produce some of this data, so you will actually get to play with this and look at how are sounds represented in the auditory system at the higher level. Okay? Now, this brings me to a natural stop, and any questions so far? So what we have done so far, we have talked about physiology, anatomy, and physics, and how sounds represented. I gave you kind of a bird's eye view of how sounds are represented in the auditory system and how we produce sounds. I don't expect that you understand or remember everything that we talk about. This is really, as I said, it's a bird's eye view of the field, but at least you get a sense of where we're coming and where we're going. You know, I mean, really where things are. Now, okay, so physiologists like Nima and Shihab and Maureen, who likes to study the vocal tract, the physics of the system and how it relates to sound, have made models and so on. Now, on the other hand, we have us, people, okay? And do you think that at any instance, me, I'm making a model of the tank or in your brain now, are you making a model of my tank as I speak, you know, a physics model, so that you can actually understand what I say? Probably not, you know, I doubt, you know. So there is a level between the physics of life and its manifestation, in this case for speech production, and the perceptual aspects of human communication. What do we actually perceive? So when it comes to sound, turns out there is three categories of perceived things, okay? Classes of things. Loudness. Well, intensity. That is really a percept of intensity. You can tell when something is loud or not so loud, okay? Well, that much you can tell. So that is a perceived, a percept of intensity. Pitch. Well, much like intensity, there is something basic about tones, you know. So So the first one clearly sounds like a tone, a low frequency tone, and the other one, falsetto, sounds like a high frequency tone. So that's a sense, in a sense, your percept of pitch, okay? Now, everything else that is involved with sound, that relates to sound, that is not intensity or tone, pitch, is timbre. So basically everything else that we don't have a description for, we put in the timbre, okay? And so timbre is a very complex field, often very controversial because it has to do with things that are not very simple to describe, like, I don't know, someone sounds nice, you know, or someone sounds angry. Well, you know, it's all in the timbre of your voice, you know, in some ways, and the pitch and the loudness. But it's actually it has to do with basically the richness of the sound. And you can, for example, you can tell the difference between a flute and an oboe just based on the timbre of the sound they produce, okay? And that is really a good example. Musical instruments, you can tell from the timbre what they are. Now, loudness. Loudness is a perceptual correlate of intensity, and I'm not going to make a phone call, but there's a little app that I have on my phone, which is an audio app, and I can pass it around, and you can talk or bang, and you can actually measure the loudness of your sound that you're making, or in this room. And basically, the sound pressure level, SPL, the scale for loudness is the sound pressure level in dBs, and loudness varies from person to person, and of course it is a function also of the sound window, and so also it's a function of the frequency. So this is frequency, and at a different window. So turns out that a sound, a 50 hertz, a 10 hertz sound to you at the threshold of hearing, to you it will have a level of, it will sound like a 7 dB, okay? And the same sound at 2 kilohertz will actually be perceived in a different way. So at a much lower dB level. So you are sensitive. Okay, I say the other way around. So where you're sensitive is basically this area here, between roughly what 500 hertz, 1, 2, 3, 4 kilohertz. Okay, that is really, you have maximum sensitivity to those frequencies. And typically these curves will move up and down, and the units of loudness are son and phone. So actually you have these devices that can measure loudness in dBs. As I speak now, roughly here at about a meter away, the loudness is about about 80 dBs. Okay, this is really of my voice to this device measured from the microphone there, and so on. And there is a different weighting here. I can pass it around, and you can make sound and see how fast actually, how loud am I in the various parts of the room. Turns out that there is a relationship between the son or the dB relatively, which is the sound pressure level that I showed in the previous slide. That is a relative scale relative to 20 micropascal, and there is an absolute measure of loudness. The absolute measure of loudness comes in pascals, which is really units of pressure. And interestingly enough, a normal talking at one distance is 40-60 dB. Obviously, when I was talking in front of my phone, I was not really talking normal. I was actually screaming. So more like here 60 on 80 dB SPL, because I was actually measuring about 80 dB, 80 SPL. A very quiet room is about 20-30 dBs. And you can change actually the scale. You can also change the integration time to really get different. And the weighting has to do with the frequency in that instrument there. So that is really all about loudness. And I think I will stop here. The threshold of pain is it is really about the sound that you get if you stand 100 meters away from a jet plane. So be careful when you're at the airport and you're trying to go on on these little planes and you're walking through there. If actually a plane comes nearby or starts this engine, that's really very loud, and actually that can actually cause damage. Hearing damage during short-term effects about 120 dB. So you actually temporarily you can really get deafened. If you have an iPhone, you can go and get this app. It's not very cheap, but take it with you to a rock concert. Probably the kind of levels you're going to see there is also close to 140 dBs. So that is really that's something that you should be aware. So let's move to the next perceptual measure, and that's of pitch. So this is really the measure of perceived frequency of a tone. This is the first work was done by Stevens and Volkmann, 1940, where they actually tried to relate the absolute measure of frequency with what humans perceive as frequency. Actually, what they did is the absolute measure of frequency change to what humans can perceive. In other words, if I give you a sound at 200 hertz, okay, and then I give you a sound at 400 hertz, okay, you can actually measure, you can actually tell, oh, that sound was had twice the frequency of the previous sound, okay. Now, if I give you now a sound at 4 kilohertz and a sound at 8 kilohertz, would you be able to actually tell that one was double, an octave higher than the other? Probably not as easily, okay? So your inability to tell the difference in sounds as a function of frequency is really called the Bell scale, and this is really a very important psychophysical scale. Do you guys follow what I just described? It's your ability to tell apart sounds at different F0, at different frequency. So let me, I just described what's written there. So this is actually this is really what the Bell scale, the Bell scale function is. So what you can see, I've forgotten I have this. What you can see here is that for low frequencies, this is almost a line. So that means that actually roughly at 500 hertz frequency, you perceive that the change will be 500 hertz. At 1,000 it goes up, but as you go to higher frequency, you can change, let's say, from 2,000 hertz to 3,000 hertz, and the perceived change will only be between 1,500 to 1.5 to 2. So as is less than, let me do this. From 2,000 to 4,000 is a factor of 2, and I only get, from 2,000 I get 1,500 mels, and I get to 2,000 mels, so I only get a factor of what? A factor of a quarter. So in one case, you're really linear, in higher frequencies. So what does it mean? This means that your ability to distinguish frequency changes at high frequencies diminishes your ability to distinguish frequency, differentiate tones of different frequency diminishes as the frequency goes up. Okay? That's really what it means. Now, why that? Well, this is the mathematical formula for that. Sanjeev, we're running out of time, I know, but I think we'll steal a little bit from Nima. 10 more minutes. Okay, so we'll okay, 10 more minutes. Oops. Next time I want this to be a 3-hour tutorial, and I'll be on time. Okay. No, okay, so why is that? Well, we skip the cochlea, but turns out actually is partly related to the way your organ of hearing works, you know. If we look at the frequency resolution of your cochlea, at lower frequencies, you know, your cochlea can be represented as a bandpass filters, you know, spread out in a uniform frequency scale. But as you move away in frequencies by above roughly 500, 600, 700 hertz, instead of now being a linear, you get these filter banks in a linear scale, you are beginning to get basically these filter banks on a log scale, okay? So essentially your frequency response, your filter banks become broader, okay, as you go to higher frequency. And hence, your ability to distinguish sounds, you know, at higher frequencies diminishes. Now, this is kind of unique to humans. If you go to, just for some biology trivia, for those interested, there is actually bats now that they have a cochlea, that they have the equivalent of a fovea, which actually enormous frequency response range where actually they have a very linear frequency response. So they can actually tell the sounds between 40 kilohertz, 41, 42, 43, 50, 60, 70, and so on, you know. So enormously, because they have a different function there, they're not really meant to really sense speech. Now, I will skip the speech encoding and telephony and move on to the next topic because it is kind of not very relevant to this workshop. But so, turns out actually, we talk about loudness, we talk about pitch, and these seem to be kind of static or quasi-static attributes or perceptual attributes that actually affect how we perceive sounds. Now, there is a whole slew of perceptual attributes that involve dynamic effects, and dynamic effects of the order of a few 100 milliseconds, you know, temporal effects, okay? And things like, we talk a little bit about loudness and duration because I said you can really integrate of longer period and it will sound more loud, or smaller period it will sound less loud. Things that have to do with detection of gaps in sounds, phase sensitivity or ability to actually detect phase, and temporal masking, forward and backward. And let me actually take that and give you a little bit of an explanation of this effect and bring back and show some of the system architecture that has been, some of the engineering work that has actually came up out of these ideas about looking at forward masking. So if you have a signal, let's say this, and you have another strong signal, which is really your masker, this sound here, separated by some delay here, turns out that the fact that you really had the sound coming before your signal, it will affect how you actually perceive the signal here, okay? And the effect is a function of time. You can have forward masking when this is called forward masking, or you can have backward masking where you actually have the sound. I mean, in this case, you have the masker and then the sound of interest. In the backward masking, you have your sound of interest and then the masker. Okay, the other way around. Okay. Now, clearly, this is something that is very important. Forward and backward masking are key are key effects that are exploited in many of the MP3 coding that, or any coding, music coding that actually is used out there. So in fact, you know, when you play MP3 on your iPod, those that encoded the sound, so you can actually store the sounds on your iPod, really exploit the fact that your ear cannot hear certain sounds when there is a temporal gap, when there is temporal, when there is a time between the two sounds. So a lot of work, Pavel, Lehman, Jester, Bacon, Lehman is one of the earliest results, and basically what it basically if we take the example of a masker tone at 1 kilohertz and a signal, which is a masker is 300 milliseconds, white, signal 20 milliseconds, it's kind of short, but it's relevant to speech, you know, at 1 kilohertz. So what you can see is that the loudness of your signal is affected in a way that is showing this in this graph here, as a function of the delay between the masker and the signal. In other words, a sound that follows another sound affects the percept of the sound just played before. Okay? And the way it affects the loudness, the intensity, is really a function of the delay between the masker and the signal of interest. You guys follow that. Now, this is not something that you're aware of. But as I pointed out earlier, it's there and it's happening in your brain, it's happening in your auditory system. The mechanisms are still quite, you know, there's hypothesis, but people are trying to understand why this happens. And this is an example, this is an example of a phenomenon that has been used in speech recognition. And let me, now I'm, yeah.
I didn't understand what the picture meant. What is saying with it? You're saying that the intensity of that second window of tone,
right, would be affected depending on
by
the
XDBs,
XDBs, right, because of the masker.
So if you play me a tone after a small delay, which otherwise intensity otherwise is 20 dB, I'll perceive it 50 dB lower.
Right.
If it's 40 dB, I'll perceive it with 14 dB
Right.
lower. 60
Mm-hmm. Yes, yes. I mean, and so that is really, yeah, that's right. As a function of the intensity. Yeah. Yeah, I just, I'm running out of time, I guess. But, so, you know, this is really Rasta. Yeah, so that's why I brought it up, but we don't have time to go through this. So, well, I didn't say anything about the ASR. Let me take a little bit of time from Nima and we can... Okay, I want to, you know, because I think this is really... let me take a little bit of time from Nima and... Nima, let's do another 15, okay? Okay, so let's now talk a little bit about ASR, automatic speech recognition, and try to... Yes.
So I don't think you know this, but there's been a change of the lab location for the next session. It's not going back to Schaefer 100. We'll go to the second floor of this building. This is because the computer is taking place. So we'll do the lab.
Yeah, well... I'll take them later there. Yeah, not only the bus was late, the computer broke, the master server for the system, for our system broke. Okay, I'll take them to lab. Yeah. Okay, let me do this because I think some of this may be useful for things you're going to see this afternoon. So may as well just go through this. So what you really want to do now, let's see how some of this knowledge that we've talked about has anything to do with the way we actually build automatic speech recognition, how this perceptual production model stuff. My talk, I'm going to put on the internet. There's a lot of stuff, vocal tract normalization. You can go and read all about Mel scale. I want to talk. I'm going to for the next 15 minutes, we'll talk a little bit about automatic speech recognition, the very basic ideas, and then we'll talk a little bit about masking, forward masking, and what kind of models have been used, built in the speech recognition systems today that actually capture those phenomena and have improved the performance. So everything that we do, everything that most people do today in pattern recognition, whether it's speech, vision, serious systems, relies on a very simple idea. And it is amazing how much such a simple identity called base rule, how much impact it has. So if you have two variables, x and y, the joint probability px, comma y can be written as follows. It can be written as the probability of y given x times the probability of x. Also, it can be written as the probability of x given y times the probability of y. How many people have seen this from your probability? Very good. That's good. This is where it all starts. Now, related to that equation and inspired by that simple identity is something called Bayesian inference. And basically, it tells you, if you have data, D, and you have belonging to some hypothesis space I, and where each of the alternate hypotheses is yi, let's say E, these are the data, and the goal here is to make a machine to tell which class of phones, or F1, F2 classes belongs, hypothesis 1, F, hypothesis 2, E, hypothesis 3, okay? So then everybody around goes and speaks like this, and we have a machine actually put the data in one of these classes, okay? Each one of those classes is a hypothesis. So it tells us actually, based on that now, we can take the second half and forget about this for a second and say the probability of hypothesis yi, let's say, given the data D, given the sound that you record from the microphone, is given by the probability of the data given yi times the probability of yi, we're going to have a name for this, divided by the probability of the data. If you look at this, it's nothing but rewriting the second half of the top equation in a hypothesis testing paradigm, okay? Now, this is really the basis of Bayesian inference. And there's funny names and fancy name. This is called a posteriori probability. The probability of the hypothesis given the data is your a posteriori. You have something called the likelihood, which is the probability of the data given the class, and the prior probability, which is the probability of the class. Now, the probability of the data, I can actually take my probability of the data given the hypothesis, multiply it by the probability of hypothesis, sum it for all the hypotheses, and basically that gives me PD. Okay, it's just a nice way, because often what you will have in an experiment, you have actually the individual components. So if you want to get PD, you have to sum for all the components in the hypothesis space. Okay, and that gives us PD. Okay, a lot of what you're going to be doing in this workshop is really using this. Okay. I mean, that is really the essence of many things that you'll be doing. And let's take now this example, the Bayesian inference, and see how we actually can use it to do speech recognition. Clearly, the book isn't that good that every time we have something important, it so happens that that person is here. So the book that you can learn all about statistical pattern recognition is really Fred Jellinek's book. It's a classical book written here at Hopkins. Is a gentleman that talked to you. Did he give a talk? Did he introduce? No? Okay, he didn't come yesterday. You're going to see him in a couple of weeks when he will start the workshop. is here. A lot of the mathematics of how to do speech recognition is in this book. And the key, going back to inference, the key question that we ask is which sequence of words W, where W1, W2, W3 are words. W1 is a word, W2 is a word. Okay, each one is a word. Among all possible utterances of all possible words that one can say, most likely produced the observed signal X. Okay, so it's kind of a generative model of speech recognition. We start and say, we observe a signal in the microphone X, those wiggles. Okay, which words produce those wiggles on the microphone? So this is really, what is this called now? Based on our previous slide.
Probability of WI given.
Yeah, but what name did we give it? The likelihood. Okay? Okay, now we can actually use the same, So what we want to do is find the estimate sequence of words W's for all possible sequence of words. Now that's a hard problem. Imagine how many words you have and how many different ways of saying each word you have. You know, you really have to have, this is a big search. It's a hard problem. So it's a lot of good algorithms, and so most of the work in speech recognition is really evaluating that. We can rewrite the equation. Above as the probability of the utterance Wi given the signal S is evaluated from the probability of signal S given the utterance Wi. So we can rewrite that using Bayes' rule, or our formula before, and now we have two actually terms here that we need to maximize the product. The first one is the sorry, that was a posteriori. Again, I tried to show you something and then I showed you the wrong thing. The probability of the signal given the utterance, this is really what we're going to call the acoustic model. This is actually going to be our likelihood. And the WP of W is basically the probability of the utterance itself. And this is going to be referred to a language model, and that would be the prior. So what does it basically tell you? It tells you that if you heard a sound, what this formula, and we need to evaluate that equation over all possible utterances and everything. What it basically tells you, if you have an acoustic signal, if you have some acoustic X, that X is a result of some brain somewhere generating a set of words W's, okay? Now, it tells you now that which sequence of words W's the brain generated is really comes from something which we're going to call a language model. In other words, if I go is three words that actually will occur quite often. If I, two words, diagram, that's going to be called a diagram. The probability of listening to people talking and hearing if I is very high. On the other hand, the probability of listening to people talking and hearing the words if go is low because it's not grammatically correct. Okay, so that has a low probability. That's the prior. If go, the probability of if followed by go has a low prior. I don't know. Maybe the language model people will tell me the if go and if I go, the priors are going to be the same. But actually, I think there is a difference. You know? So if I go, that's another two words following each other that have a higher probability. So this captures that. And this is really captured by acoustic models that we have to make, and they are complicated, complex mathematical structures using hidden Markov models. Now, I like to, going back to our ASR system, I would like to model it as this little cartoon diagram, where you have a machine. You have a machine that actually computes this. You have your input X. You have your estimated, your predicted series of words W hats. And somewhere in the system, you have K row, where K row is some knowledge that you actually build about in the machine that the machine is going to use to really evaluate future instances. This is what you're going to train the machine to really do. And you have actually two kinds of things. You have K and R. K is the structure of your models, whether they're graphical, whether they are trees, whether they are HMMs, or partition surfaces, and rho are the parameters of your model. So there's two things that you really need to learn, and normally you can actually learn them from data. You can learn both the form, the structure of your model, that is, and the parameters rho of your models. And so the training, you'll be designing models, you'll be training them, and then you'll be using the models to actually, and the machine to actually evaluate your problem. Now, in a speech recognition system, there is three sets of processing. There is three layers of processing that occur. The first, you have the microphone. That's where you convert the signal from a pressure wave into an electrical signal in an environment. And you can have an array or a single microphone. And you can actually make models for your microphones. You can learn the models and so on. Then you have feature extraction. This is really where you take your signal, the wiggle that you see, and you make it, convert it into numbers so that you can actually do something with those numbers. And then finally you have your classifier, which is typically the machine that I just, this maximum likelihood or a map, that's how they call it, machine that actually will do the classification and whatever else you want to do. Now, let me take, this is what I was supposed to spend most of my time on, on this, but it's okay. So typical acoustic front end will take the speech sound, which is going to be discrete samples in time. How many people have signal processing? Okay. So you're going to get basically the frame, a period of time for the waveform, and that period of time is roughly 25 milliseconds, 2.5 times 10 milliseconds. So you're going to get, in 25 milliseconds, you're going to have an A to D converter, and it's going to basically get you 256 samples. It's going to take the signal and convert it into digital numbers, 1, 2, 20, 50, 256 for a period of 25 milliseconds, okay? So every 25 milliseconds, you're actually going to get these samples, okay? Then, so forget about the signal number. Forget about the wiggles now. They're just all numbers, okay? Those numbers, actually, you're going to do a Hamming window and FFT. This is digital signal processing. You're going to turn them into 128 numbers. So every frame, every 25 milliseconds, you basically get, at the end, 128 numbers. From these 128 numbers, you're going to decide what words did I say. Okay? So you have every 25 milliseconds, you're sampling, and those are the data you actually get into your system to really decide what words you're going to say. Now, that's a lot of numbers. In other words, these are too many numbers to really make decisions on. And there is a problem that maybe you'll learn a little bit more later, that if you have too many numbers, your feature vector is too big, your system is going to have too many parameters, you're not going to have enough data to train your system, and your system is not going to work. So the first thing I'm going to do is the following. These numbers here correspond to frequencies in a spectrum. Okay. The first thing I'm going to say is the following. We learned something about Mel scale, and what we learned is that actually we can take, for low frequencies, we can make the bandpass filters at a regular linear frequency scale, and for high frequency you can compress. So we can actually get the 128 bins, frequency bins coming here. 128 numbers, each one of these numbers corresponding to one frequency bin, and group them together, so now we get only 24 frequency bins. Now these 24 frequency bins are the bins that I showed earlier, which are linear in frequency for low frequencies and logarithmic in high frequencies. So now, instead of 128 samples, now I get basically 24 24 numbers. So now, I started with 256. I did the FFT. Anybody knows why 128?
Because you throw away the imaginary.
Because I threw away the imaginary. And by throwing away the imaginary, what happened too? I lost all the phase information. Okay, so I've thrown away phase, and I keep the amplitude. You know,
I thought it'd be you throw away the negative frequency coefficients.
Sorry, that's what I meant.
the negative, but also the imaginary.
Okay.
Negative frequency, yes. I keep just the amplitude.
So the magnitude?
The magnitude, yes. So then I get 128, then I apply this nonlinearity that actually compresses the MEL scale into 24 numbers. And now which is really a lookup table, it doesn't change the dimensionality of the data, it just puts the data in a different kind of format, and there's a reason for that you see in the next slide, why it's useful. Then I get the 24 numbers and I make them, compress them further down into 12 numbers by using the discrete cosine transform. Again, try to really get my features down to a reasonable set of numbers. So I started with 256 samples from the A to D converter, 256 numbers coming into my computer, and I end up with 12 numbers. Now, someone may say, this is pretty ad hoc. You know, why did you do this? Well, I can justify this, and I can sort of justify this on basis of some coding. I want my representation to be independent. You know, my numbers to be statistically independent, and some this will do it. But it's actually, I have to admit, this is pretty ad hoc, but it works, and everybody is using it. And this representation is called MEL frequency Kestrel coefficients. Okay, so when you read somewhere, or in the toolkits that we'll be using about MFCCs, is basically taking 256 numbers and producing 12 numbers, which are really your Kestrel coefficients. Now, what do we do actually in speech recognition? We do something else. As you see, things got smaller, features got compressed to 12. We do one more step now, and the one more step now will just increase the number of features. We take the derivative of the features in frequency and another derivative, and that equivalent to actually producing now 13 plus 13 plus 13, 39 features, and we use those features in our system. So we start with 256, and at the end of the day, we get roughly 39. Again, an ad hoc step. Alternatively, you can say, instead of actually taking the derivatives and derivatives, I will take I'll take 9 frames, concatenate all the numbers together, basically these numbers together, 13, 13, 13 for 9 frames, and then do a transform there. It's called LDA, and that transform will find actually the linear dependencies among the features among the various features in time that would actually give me a better representation than just taking ad hoc derivatives and derivatives. Now, this is really the standard front end that you use for speech recognition, and it is perceptually related because at some point we have this compression here, which is related to the percept of pitch, the MEL scale. Okay. So, at some point, the people that they're saying, oh, we can use speech recognition and it's great because we can actually use human perception for our systems, they won, you know. They say, hey, every system uses that. Now, a couple interesting questions. Is there a unique MEL scale? Is the MEL scale unique? Can you discover that nonlinearity? Can you actually get a lot of data, process the data, and discover what the nonlinearity is? The answer is yes, you can do it. It's in the talk. We've done it in a workshop like this a few years ago. We actually discover what is the nonlinearity. Turns out there is a MEL scale, which is more appropriate for male, and that's why it's called male scale. And there is a male scale for female, which is very different than the male scale for males. This is from data. So all kinds of things you can do here. And I think at this point, Sanjeev came here and says, time for you to go.
I came here to say Nima is crumbling, and you're taking away my time.
Nima is crumbling. Okay, so at this point, I have done at least part of my task to tell you something about perception, something about audition, something about production, and relay that in some very rudimentary way to the way we build ASR systems. The next slide comes about PLP and raster, but we're done. You can read all about it in my presentation, or you can come and talk to me later if you're interested in this. Now, go and have fun and learn something real in the lab.